and welcome to the June Recreational Astronomy Night meeting of the Toronto Centre RASC. My name is Paul Markov. I'll be introducing the speakers this evening. And the speakers are, in the following order, Arnold Brody presenting the sky this month, followed by Macnaughton teaching Neil how to land. And finally, Richard Blackman will wrap it up with Fiddling with Focus, the do-it-yourself way. And also, welcome to summer. I hope it's here to stay. We got some clear skies already. I wanted to ask who's here for the first time or a new member. Either way, show of hands. Very good. Welcome. Hope you enjoy the presentations and to see you again in the future. And I think that's all. Without further ado, I'll call on, Ralph Chu, I should say, to do a brief memorial.
Thanks, Paul. I think we were all very, very shocked to learn of the sudden passing of Charlene Norgrove after our last meeting. We don't really know what happened to her, but we do know that she died very suddenly sometime on the afternoon or evening of May 29th. And we'll really feel her passing. We'll always remember her as a very, very enthusiastic and encouraging individual who went out of her way to, share her love of astronomy with all members. And again, she always had a good word to say about everything. And in fact, on our YouTube channel, there's a very nice memorial to her that is appended to one of the clips in which she had her last participation in our meeting by asking a question of Ed Trace about her condo and recycling. And there was, she had a humorous entree into that, and we got a lot out of that exchange between her and Ed. So again, something to remember her fondly by. I'd ask you to rise in a moment of silence to remember Charlene. Thank you. Okay.
Thank you so much, Ralph. And I'll pass it over to Arnold Brody to present the sky this month.
Thank you, Paul. Oh, that sounds loud. Is that okay? Very good. Okay, so I'll be talking about the sky this month between now and our next meeting on July 16. And I'll talk about the summer solstice, that's in a couple days, the constellations at this time of year. We'll visit the solar system, and rather than talk about space missions, I thought I would dispense with that, instead talk about Jupiter and Saturn. They've been in the news lately with some interesting changes that are happening, and since they are now prime time targets for this month and next, it's appropriate that we pay a little attention to what's going on those gas giants. I'll then go into deep space, and we'll finish with a easy citizen science challenge for us all. Okay. Okay, summer solstice. The sun crosses the equator on its trek northward in 2 days. Friday, June 21 at almost noon Eastern Daylight Savings Time. That puts us in the narrowest portion of the hourglass shape. There we go. In this 2019 almanac by Sky and Telescope. As you probably know, it's officially night when the sun is 18 degrees below the horizon. So astrophotographers have the smallest window of the year for taking deep space pictures. In true darkness, around 4 hours is available. But you don't need to wait for total darkness to enjoy observing the night sky. Jupiter, for example, is so bright. You can start observing it as well as double stars and bright clusters during astronomical twilight. So if we include astronomical twilight for observational astronomy, we can add a couple of hours to our window of time. This is the whole sky from southern Ontario at midnight tonight. The Sagittarius arm of our Milky Way is now sweeping across the sky from Sagittarius through Aquila, Cygnus, all the way up to Cassiopeia. And this yellow plus sign represents the center of our Milky Way, the nucleus. It's largely, you can see how it's fat. The glow of the Milky Way is largest there, but the actual center is largely hidden by intervening lanes of opaque dust. The spring constellations such as Leo and Virgo are beating a hasty exit to the west, meaning the next 30-day period is your last chance this year to catch the galaxies in the area bounded by Ursa Major and Leo, Virgo, this area here. You'll have a chance still to catch those galaxies. And we'll talk about the summer DSOs rotating into view in a few minutes. As for the sun, we reach aphelion on July 4 at a distance of 152.1 million kilometers. That's 2.5 million greater than the average distance, the astronomical unit, or AU, which is 149.6. So we're as far as we get from the sun in a couple of weeks. And we're just about finished with solar cycle 24. A panel of experts assembled by NOAA and NASA concluded that the minimum marking the end of the current cycle will occur sometime between July and this coming September. They say the next peak will occur sometime between 2023 and 2025 with 95 to 130 sunspots, similar to solar cycle 24 that peaked with 116 sunspots in April of 2014, right about there. Now, there's going to be a total solar eclipse passing through the U.S. and the Niagara region in 2024, right in the middle of that predicted maximum. And that could produce a spectacular solar corona reaching out into space all around the sun, as opposed to just wings stretching out from the equatorial region like many of us saw in 2017 during that eclipse in August. Now, at the OSC solar observing sessions and elsewhere, we can now tell our visitors that we are now at solar minimum. And in order to receive enough solar particles to trigger auroras, we would probably need a large coronal hole to rotate into view facing us. Solar wind can accelerate through a coronal hole. Coronal holes are generally visible during solar minimum, and they're typically at the north and south poles of the sun, but sometimes they will occur in mid-latitudes where magnetic field lines fail to reconnect. And the particles in the corona can jump out into space at twice the typical speed of solar wind. And because coronal holes can last for a couple of months, they can rotate more than once into view, so we have an opportunity to predict loosely whether or not we're going to see some activity based on the coronal holes. Now here's a sequence starting from June the 5th, and you'll notice that we do have holes at the top and bottom, but here we have a finger stretching down, and here's another representation of it in simple graphic form. And now what we'll do is we'll step through this and watch as the sun slowly rotates that finger swept across. Some radiation was felt, was experienced, not necessarily enough for auroras. And finally, at June 15, we seem to have another hole starting to develop here. So it is possible to get mid-latitude coronal holes, and if they are large enough, we might get enough in the way of solar radiation, solar wind, to produce some auroras. But that's iffy. We'll just have to wait and see. Okay, as far as the moon is concerned, prime time for observing and astrophotography are the last week of June, when I'll be in Algonquin Park, and the first week of July, when we have a new moon occurring on July 2. There's apogee on the 23rd and perigee on the 5th, no longer connected to either the solar full moon or new moon. Now, speaking of the new moon, there will be a total solar eclipse on the 2nd of July. It'll pass over the Pacific Ocean, northern Chile, and central Argentina. And then 2 weeks later, there will be a partial lunar eclipse over Europe, Africa, Central Asia, and the Indian Ocean. And I'm curious to know if anybody's planning to travel down to South America. We have a few in the room here going to South America, and perhaps a few people online that may have their tickets purchased for this trip. And if you do, here is the center line running through Chile and Argentina. I believe this is where the eclipse lifts off the surface. And if you catch it here, the duration is 2 minutes and 30, about 2.5 minutes. Basically the same duration that we had in 2017 back in August for that eclipse. So you'll have the same duration, especially in this area here. If you are unable to go to South America, you can watch it online. There's a website that you can visit on the day of the eclipse and watch the eclipse through the live streaming. And for us here in Toronto, the totality would begin at, well, that's 20, so take off 4, that's 16. That would be 4 o'clock, 4:30 in the afternoon on July 2, if you want to sit down at your laptop or whatever and watch the eclipse. Now, for observing the moon, as far as the lunar X and V are concerned, not this time. That happens at like noon our time when it's over Europe, so it's their turn, not our turn for the X and V. And for libration, we just finished a significant libration here in the southeast limb. It was tipped our way the last 6 days or so. But it'll happen again in July, the 9th and the 10th. Your chance to catch some of these oval dark craters. And the northeast limb, or northwest limb, I'm sorry, will be tipped our way at the end of June, June 27th through the 30th. And fortunately, when these two sides of the moon are tipped our way, they're also illuminated. So you have an opportunity to sketch or photograph or just take a good look at sides of the moon that you don't normally get. And the moon, weather permitting, we can watch the moon make some interesting moves between July 12th and the 15th. On the 12th, the moon dances the ring around the rosy with Jupiter and Antares. It then does a do-si-do and jumps to the other side of Jupiter the following night. By July 14, the moon has waltzed about halfway, almost exactly halfway between Jupiter and Saturn. And these three will form a striking line of bright points, virtually in a straight line, virtually equally spaced, stretching 30 degrees across the sky. That should be quite a sight. And the dance ends with the moon picking Saturn as its partner on the 15th, when the two of them are just 1.5 degrees apart on the 15th. Here's our inner solar system as of tonight. And from Earth's perspective, Mercury and Venus lie on opposite sides of the sun. Mercury is east of the sun, so it should appear low in the west in the evening, setting soon after the sun. Now, Mercury will actually reach greatest elongation east of the sun on June 23, then race between us and the sun towards inferior conjunction on July 20. And Venus, well, it appears west of the sun, meaning it is the morning star, up in the east before sunrise, but Venus is racing around the sun faster than we can catch it, or faster than we can chase it, so Venus will rise closer to the sunrise over the next 40 days. It's getting ever so close to the sun until it reaches superior conjunction in August. And a line from Earth through Mercury will zip right past Mars, suggesting that those two planets should appear very close together as this period begins, and indeed they do. There we see Mercury and Mars just a degree apart, half an hour after sunset tomorrow. So if you happen to have a good view to the west, you might be able to catch a picture of those two planets close together. 2 weeks later, with Mercury 3 3/4 degrees away from Mars, a thin crescent moon joins them. So here's your July 3 challenge. Find the thin crescent moon. Probably need binoculars. Those of us that were up at the CAO for the spring work party in the first weekend of May, we actually caught that moon in the same less than 2 days old, just a day or something. We managed to catch it with binoculars. It was spectacular. I think when I dropped the binoculars down, I saw it with my eye. I think I did. So it's doable. Let's just hope that we have a good weather that night to give it a try. And here's Venus at 5 a.m. tomorrow morning, just ahead of the encroaching rays of the sun, which will rise about a half an hour later. And here I show you Venus's orbit to illustrate how far it has moved down from its greatest elongation west back in January. Venus will be increasingly harder to view as it slides closer to the sun, eventually reaching superior conjunction in August. And I think it takes about a month to get out of the sun's glare, so sometime in late September, early October, it should start rising as the evening star. Here's the outer solar system, and here we see Earth and the outer solar system planets, as well as Ceres and Pluto, as of tonight. Notice how Ceres, Jupiter, Saturn, and Pluto all lie roughly in the same direction from Earth, opposite from the sun, and should therefore appear fairly close together in the south around local midnight. And since Jupiter is only 2 weeks past opposition with Earth, it's not surprising that it's just west of the Sun-Earth line. And Saturn will be our next opposition planet, with Earth sliding between it and the Sun on July 3, just about 3 weeks from now. Uranus has emerged from the glare of the sun and is now rising around 2:40 in the morning, and will continue to rise earlier each day as the Earth orbits towards Uranus, and Uranus will be in opposition in late October. And Neptune, did it again. There we go. Neptune, appearing west of Uranus from Earth's perspective, rises an hour and a half ahead of Uranus and will reach opposition in September, early September. So looking south around local midnight, there indeed we see Pluto and Saturn appearing close together east of the meridian. Here we have them. And Jupiter and Ceres lie west of the meridian, having just passed opposition recently. Jupiter 9 days ago and Ceres 11 days ahead of Jupiter. So it appears a little bit further west. A drawback of summertime oppositions for us here in Ontario is how low the planets rise above the horizon. Notice how low Jupiter is when checked against the altitude scale on the meridian, just around 23 degrees up or so. Not very high. That's the downside. And the ice giants, Uranus and Neptune, are rising early in the morning. You'd want to wait a couple of months before you pay them any attention. They're just so low and so far. A little bit later, when we get closer to Uranus, it becomes a nice round circle in your telescope that we can look forward to, but probably not until late summer, early fall. Now, the gas giants Jupiter and Saturn are front and center, if a bit low this summer. And here are a couple of Jupiter moon events you might enjoy watching or imaging. Let's see if I can do this way. Here we go. On July 4, Io transits Jupiter with its shadow doing the same, about 90 minutes behind. There it goes. There you see the shadow. The moon and shadow transit runs for more than 2 hours. A good photo op would be around 20 minutes after midnight, which we're getting to pretty soon, when the shadow would still be well within the limb of Jupiter, but Io would be out in space off the limb, somewhere around there. And that would be a good photo op, I would think. And for something completely different, you might like the peekaboo Ganymede plays with Jupiter on the 7th of July. Here we see Ganymede behind the limb of Jupiter. And it only takes 15 minutes after Ganymede emerges from behind Jupiter that it hides again, this time in the shadow of Jupiter. There it is. It's coming out. It's emerging from behind Jupiter. But keep an eye on it, and it starts to disappear very soon. It slides into the shadow of Jupiter. There it goes. Gone. And I think this one is begging for some time-lapse photography. Yeah, that should be fun. And Saturn is at opposition on July 9. And its rings were at greatest tilt of 27 degrees just 8 months ago. So it's still highly tilted, hiding the South Pole during this year's apparition. When at opposition, Saturn will remain low in the sky due to the shallow path of the ecliptic on our summer nights. Meanwhile, you may have heard or read a few months ago that Saturn's rings are transient and are raining down on the planet and will someday cease to be. But not to worry for us, this will take a few 100 million years. But it is fascinating to think how Jupiter and the other gas giants may have had Saturn-like rings of their own in the past at one time.
New NASA research indicates that Saturn's iconic rings are not only younger than previously thought, but also that these rings are actually disappearing at an extremely fast pace. The research found that the rings are draining away toward the planet as a dusty rain of ice particles. Saturn's rings consist mostly of water ice that ranges in size from microscopic dust to large boulders. Ultraviolet light from the sun and plasma clouds coming from tiny meteoroid strikes charge the icy dust, which then becomes bound to Saturn's magnetic field and pulled into the planet by gravity. This material rains into the planet and begins to disintegrate, allowing it to react chemically with the electrically charged part of Saturn's upper atmosphere, the ionosphere. The ions glow in an infrared light as part of this process if the rain is light, but the emissions dim if the rain is heavy. This was observed using instruments attached to the Keck telescope in Hawaii. The rate of disappearance in this ring rain study has allowed scientists to infer that Saturn's rings formed less than 100 million years ago. This means Saturn wasn't born this way, as the planet is known to be over 4 billion years old. And when the ring rain data is combined with observations made by the Voyager 1 and 2 missions, scientists from NASA Goddard are able to estimate that the rings will be gone in 300 million years. So if this rain doesn't go away, Saturn will be ringless another day.
So here we see a video depicting how those rings would gradually disappear over the next 300 or so million years. And they may eventually be reduced to the barely visible thin string-like rings visiting spacecraft have detected circling Jupiter and Uranus. So maybe 100 or so million years ago, Jupiter and or Uranus had impressive rings too. It's possible. The image of Jupiter on the left is what I call classic textbook. We see dark equatorial belts north and south of the equator, a bright equatorial zone, and a football-shaped great red spot as wide as 3 Earths. On the right, we see the current Jupiter, as imaged by Christopher Ho 3 weeks ago from Cebu City, Philippines. The equatorial zone has darkened considerably, while the south equatorial belt has lost much of its color, becoming more of a white belt. And there are some interesting development in and around the Great Red Spot. The spot itself has become much darker as it morphs from an oval to a circle, while narrowing to maybe 1.5 Earth diameters. And it's time for us presenters to fix our presentations that say it's 3 Earths wide. I had to do that for a presentation last week. Notice the dark stripes surrounding the spot. These lines here. Notice that? And they stretch eastward. And to me, it looks like the Great Red Spot is a pool of mercury sitting in the base of a thermometer. What's going on here? Well, the close-up by Christopher Ho gives us some clues. First of all, we have pieces of the red spot breaking off. These flakes are then slammed by jet streams that race around the red spot and shove that material down to the edge, where another racing jet stream will grab that and send it to the east, which is what we're seeing here. And another jet stream this way will grab more material and send it that way. So it looks as though it's bits of the red spot being dragged out and circling the planet. And here's Clyde Foster's annotations of what's going on at the red spot. And if you can see it here, there is the direction of the equatorial belt jet stream. It slams right into the red spot and circles above it, grabbing whatever flakes, and here's another one peeling off, a little flake there, slamming it down to the bottom here where the remnants of the great red spot flakes are crushed, and then jet streams, here's another one going that way, will grab it, stretch it out. So it's rather dynamic. We're seeing a lot of stuff here, a great amount of turbulence behind this spot as this spot is changing. Now, it's not really getting faster. That's what a lot of us thought.
Jupiter's appearance is the result of its swirling interior of gases and liquids, producing a tapestry of colorful cloud bands, as well as the iconic Great Red Spot. The Great Red Spot is a gigantic storm. It's an anticyclone, and with no landmass on the planet to slow it down, the Great Red Spot has raged for over a century. But scientists studying the spot have noticed that it has been changing over time. The color is deepening, and it's actually shrinking and getting rounder. Those studying it expected to therefore see the wind speeds inside the Great Red Spot increasing as the storm shrinks, like an ice skater who spins faster as she pulls in her arms. But this isn't the case. Data reveals the storm isn't spinning faster, it's actually getting taller. You could think of it like working with pottery. As the wide lump of clay spins, forces within are driving it taller. So from our perspective, looking down on the clouds, we see the spot getting smaller and rounder. The Great Red Spot used to be big enough to fit 3 Earths. Now, it's just a little over 1. These discoveries were made by analyzing data from numerous NASA missions, including Voyager, Hubble, and most recently, Juno. And through more investigations, scientists hope to unlock more secrets of the mysterious Great Red Spot.
Whoops. Here's one more image, fascinating image. This was posted by NASA on their picture of the day on June 10 with the description that this darkness typically dark features are lower and the brighter features are up higher. So it's very possible that this dot, this black eye looking back at you, is actually a deep hole in the clouds, although that is at this moment still conjecture. This picture was taken by the Juno spacecraft when it was 15,000 kilometers above Jupiter's cloud tops, and it's going to make another close pass again in July. So maybe we'll have another look at this eye looking at us. Now, out of this, out into the rest of the solar system, how about meteor showers? Well, there are none at this time. Please check back next month. How about comets? Well, my deepest regrets, but I'm afraid there are no easily observable comets at this time. How about auroras? Well, you know, we're at solar minimum, right? So there are a few sunspots, if any, no CMEs, maybe if a coronal hole is really big, maybe. And if you'd like to keep your hopes up and you want to stay on top of this, there are two websites I strongly recommend, spaceweatherwoman.com and auroraforecast.com. You can put those on your favorites and keep an eye on what's going on with the sun, but I wouldn't expect auroras at this time. And the same for lunar and asteroid occultations, were none at this moment. How about asteroids? Well, here we have something. Here are 4 asteroids that will be passing opposition during the next 30 days. The brightest of which is Melpomene. It's number 18 in the list, and it will be as bright as 9.6 on July the 2nd, somewhere around here-ish. Maybe around there, that dot. These others are also reaching opposition, although they're much fainter at magnitude 11 or fainter. And you can go to this website listed at the bottom of the screen here if you would like to visit and learn more about these great charts, very good maps, and so on from that excellent website that I suggest you give it a look. The ISS, we have lots of visible passes. I'm simply showing you 5 of them that are most overhead, the highest ones that reach the greatest altitude. Here's one on the morning of July 16. It's 10 minutes long. It almost looks like it's very, very close to the zenith. It will reach magnitude -3.9. And then later that same evening, it makes another pass, this one lasting 11 minutes. As you may know, heavensabove.com is where you want to go to create your own predictions. Key in your location so it knows where you are, and it'll produce charts like these. As far as lunar transits, there's a great website here, transitfinder.com, and I went there, and the first thing I did was choose the Science Center as the location, which produces these numbers for longitude, latitude, and altitude. I then key in the range to search. That was the biggest range I could grab at that time, and I said I'm prepared to go 80 kilometers, and then I calculate, and this is what I got. A lot of transits of Jupiter across the sun or the moon. I picked out 4 that I thought might be of interest. This one is kind of interesting because this one here on June 22nd, it's in the daytime. The ISS is crossing in front of the moon, so I'm curious as to what would that be like if the moon is up. The part of it would be lit. Would the ISS be a silhouette as it passes in front, or is it also seeing sunlight? I really don't know what you would get there. But here's one that might catch your fancy. This one is a solar transit on July the 2nd, the same day as the sun eclipse, with CAO smack in the middle of the center line. That's 10 o'clock in the morning on July 2nd. If anybody's up there and wants to give that a try, put your telescope on with a filter on the sun and see if you can get put it in movie mode, because it'll zip right through the sun really quickly. But you might be able to capture some frames of silhouettes from some CAO. And it also, it also passes through the Whitby Oshawa area. And here's one more that goes through Port Perry and so on. Again, transitfinder.com is the website that will generate these charts for you. And for deep sky, Here we see this week around 11:30. We have an unusual opportunity to see the spring stuff and the summer stuff. In fact, if I draw a line here, everything to the right I would call memories of springtime, where you still have an opportunity to catch the galaxies that are in this oval area. But on the other side of the line, we have the Milky Way rising and bringing with it a lot of deep space targets of a different nature. We have globular clusters marked by circles with a cross in them. All kinds of globular clusters because they concentrate around the galaxy's core, which is right about, where's Sag? Yeah, here's the core of our galaxy. So it's not surprising that we see globular clusters on either side of it, right? And then the Milky Way itself, where it gives birth to stars, that's where you would expect to find globular clusters. And there's a wealth of them right along the arms of the Milky Way, noted with dotted circles. There's also planetary nebulae. Of course, if the majority of stars are along the arm of the Milky Way, that's where you would expect to find other things such as stars passing on. And those would be the planetary nebula that we have, like here and elsewhere, a few of them. So you have an unusual chance, is the way I like to put it, an unusual opportunity, any clear night over the next couple of weeks, to look at anything you want. You can go for galaxies, you can go for globular clusters, you can go for planetary nebulae, and you can also go for all kinds of nebulae, such as, here's a slide from my March presentation, where I'm showing you the wealth of galaxies in the Virgo cluster, so you can catch those with anything from a small telescope up to a big, of course, the larger the better. But even with a 6-inch or 4-inch telescope, you can catch the Messiers in that group. And here's a beautiful globular cluster that was posted by Sailu Nemena. He took this picture from the Sulor Observatory, the SLO Observatory up at CAO just a few days ago. He posted it on our forum on June 12. That's a fantastic picture. And globulars are my favorite for deep sky. They're so impressive. And the globular clusters here, I'm showing you 9 of them stretched across either side of the center of our Milky Way. There we have a few on this side, a few on that side, Messiers. And on the next slide, here's information as to where they are, their right ascension declination, some notes about them. You can get this by downloading the presentation. It'll be available on our main website within a couple of days, I would imagine. And you can download this and you'll have yourself an observing list to go to work on globular clusters. Open clusters are along that line as well, because it's the Milky Way where stars are born. That's what open clusters are, newly hatched stars. And here we see 6 of them, and on the next slide, information as to where they are. And as far as nebulae goes, you've got a choice here. You've got the dark nebulae, such as the Rift, racing right through the Milky Way. That's the stuff for future stars. As far as current stars that were just born, you'll have emission nebulae, such as M8 and M20 and NGC 7000, the North America nebula. Those are places where new stars have been born, and they're so hot that they cause the gas and dust around them to glow. And then at the end of their lives, we've got a few sun-like stars that have passed on, M27 and M57. So you have all kinds of nebulae representing stars at different phases of their life available for you. And here's a chart showing you their positions and some notes about them. And finally, for Globe at Night, this is a simple exercise that I promise I'm going to do it, and hopefully many of you will do it as well. It's simple, it's easy, and it involves Hercules. This is a project that runs from June 24th through July 3. So during that time frame, go outside and look at Hercules and decide which of these charts represents your sky. How much of Hercules can you see? Is it like this? Is it really poor like that? Are you somewhere where it's very dark and you get to see a lot of stars? So choose which of these pictures represents your sky, and then you go to this website to key in the date and time, click on a map as to where you were observing from, key in some information about your observing site, choose which of those magnitude charts represents your sky, what were the clouds like that day, and description about this, the weather conditions, how was your sky, and then scroll further down and click submit. And I promise to do that. Hopefully many of you will do it as well and participate. And I think that wraps it up. Lots of sources of information. Any questions, please? Ron.
Great visuals. Anyway, I noticed you showed an image of the sun saying that these are the holes, but I don't see that when I look at hydrogen alpha. Is there a particular type of filter that brings that out, or is that something that professionals need to manipulate things for?
You've stumped me.
Okay.
I honestly don't know. Sorry. Who else wants to stump me? Here's your chance. I guess that's it then.
Images are basically ultraviolet images, so, or high ultraviolet images. That's all. So that's the only way you're going to be able to see them.
Well, thank you for that. All right.
Thank you very much, Arnold, for a great presentation again. All right, our next speaker.
When I was younger, I was so fascinated with the moon landing. And what they did was just so incredible. And I heard Al Nagler talking, and he often mentions his experience in the Apollo program. And I piqued my curiosity, and I did some digging, and I found virtually no information about what he did. And I decided I was going to work to learn about the program he was in, and to me it's an amazing story that's not been well told, and that's why I'm giving presentations tonight, and I hope to end up with a magazine article. So this is about teaching Neil to land. I'm going to start with some diagrams from above the moon, and the Earth is in this direction, and the moon was about 2 days off being first quarter, and Tranquility Base, when it was landed, the sun elevation was about 10 degrees, so they showed lots of shadows. The orbit of the command module was almost circular, about 110 kilometers up. And at a certain stage, they released the lunar module, did all sorts of checks, and then it was pointed at exactly the right direction. And it fired for about 30 seconds, and that put it into a different orbit. So instead of being 110 kilometers up, it ended up being 14 kilometers up at the other end of the moon. Then they had power descent initiation, which means they fired the rocket of the lunar module all the way down until ground. This is a great painting, except it shows the lunar module going towards the sun when it really went away from the sun, but artistic license. This diagram shows the altitude when they started firing the rocket. So it was 14 kilometers up. It went about 500 kilometers across, and this goes 8 minutes and then another 4 minutes to do the final landing, and that's the last 10 kilometers. The crew had to work together with incredibly complicated things. They had computers, and I'm sure most of you have heard that they kept getting these alarms that were saying the computer's overloaded. And the computers they had were about equivalent to a PET or an Apple II. Anybody have one of those? Yep. Except for one difference. These were programmed, the capsule computers were programmed that if the computer's overloaded, it ignores the least important stuff and it keeps doing the important stuff. And other than that, they would have had to abort because the computers got very overloaded. So eventually the capsule tipped over to the point where the commander could look out, and he thought, oops, Houston, we have a problem, because he was going to land either in West Crater or over a series of rocks that were distributed from the crater. So Neil, as all commanders did, took over personal control over the landing. Up until then, it was a computer program. And he had to go maybe another kilometer after, and eventually found the Apollo 11 landing site. And he finally touched down, and he told the world that the Eagle had landed, and Volkswagen got one of the most brilliant commercials ever. This is the display at the Smithsonian in Washington, D.C. Right by the front entrance. This is what you see. I understand they're changing it, but I don't know what it is now. This is a lunar module, one of the earlier ones in the series. None of these were recovered. When they went to space, they were crashed into the moon or sent in orbit around the sun. So this is an older model, and they made all sorts of changes, up to 100 a week at one stage in the program. So probably it's very different. I noticed this that is called the coal chute to direct it away, and apparently that was only installed after Apollo 11 found there was a problem with damage to the lower part. So they put it on when the new LEM was actually on top of the rocket, and it was placed there. The most amazing thing to me about the whole Apollo program is that this spacecraft, the first landing it had was on the moon. They never had any practice landings, of course, for the good reason that the rocket was powerful enough to resist moon's gravity and to slow it down and eventually land it. But you could fire that in the Smithsonian and it wouldn't even lift it against the 6 times stronger Earth gravity. So how is it that they ended up knowing how to land something they couldn't practice? And the answer is the simulators. And a whole bunch of simulators were made by NASA, but most of the Apollo astronaut practice was in this, plus the third one that I'm going to show. This is in the Kennedy Space Center. There's another simulator, set of simulators at Houston. The command module at the back. I'm mostly going to focus on the lunar module simulator. And I just want you to notice a few things. See the cylinder at the top there? You're actually going to see pieces of that in photos that I took. The other thing is, a very important part of the simulator to me is the computers. And I'll explain how the computers worked and helped with the process. And I don't think they could have launched astronauts to the moon 5 years earlier, because I don't think they had enough computers to drive the simulators and the spacecraft. This is the inside of a display of the lunar module at the Smithsonian with actual parts from the lunar module simulator. And the key in a simulator is every aspect on the inside is as the real thing. Same handles, same window sizes, same force required to move the switches, same everything. Now, here's the key, the middle line here. When an astronaut adjusts something, say to fire a rocket to change the direction the spacecraft is pointing, the simulator computers, those are the big banks on the left of the big photo I showed you. The simulator computers calculate how the spacecraft would respond, and then it calculates all the changes the astronauts would see, including alarms, the computer display, the fuel level in whatever thing you have, and the view in the window. And that's rather amazing. So I'm going to go back in history to talking about simulators to something nobody's going to expect, and that's player pianos. In a player piano, you have a piece of paper with perforations in it that are like zeros and ones, and they pass over a sensor with 88 holes, one for each key, and each hole is connected with a tube to a bellow. And when the hole passes over the sensor for that particular key, the bellow pushes the note and it makes a sound. The Link family ran that company that made it. And the son of the factory owner, as a teen, worked with the bellows and making player pianos, but he wasn't interested in his dad's business. He wanted to fly. And he ended up learning how to fly. He taught aviation. He did stunt flying. He did commercial flying, people back and forth. And because it was hard to teach to fly, he said, maybe I can use bellows technology and develop a trainer that will make it faster to teach people to fly. And I sat in the Link trainer. Those are my feet in the bottom. I have a friend who's a pilot, and he said that all these dials and switches are for a particular model of airplane at that era. And when I turn this control thing this way, the plane would tilt, and bellows would lift up the model and tilt as well, so the pilot would experience exactly the experience of flying. An early simulator. These weren't that big a deal. They only trained 500,000 pilots in World War II. And factories ran overtime in Binghamton, New York, and in Gananoque, Ontario. So this was quite a thing, and that was an early simulator. The Link Aviation Devices, Inc. had various corporate restructuring over the years, and the commercial side was sold to a company and ended up owned by CAE, which is based in Montreal, and a friend's daughter works there. Now, an important part of a simulator is the sim instructor, and my friend did that for pilots. He's now retired as a pilot, and he would plan a series of emergencies for the pilots to solve. And I asked him, Scully had to land in the Hudson River. Is that something that would be trained in a simulator? And he said every pilot, at least in his airline, would have practiced that in a simulator at one time or another. So they go through all these emergencies, and the sim instructor is rather unpopular, actually, because he keeps planning tricky things. Notice the view. Doesn't this look like this plane is flying in a mountainous area about to land in a runway? Actually, that's sitting in a suburban factory, because this is a simulator, and all these images are generated by computers. And if he wants to take somebody that he's done some practice and say, what airport do you want to fly to? And the guy might say, the old Hong Kong airport where they have to make a sudden curve to land properly. He can press in the right button, and it's that airport. But in 1960s, the computers were slow. Memory was expensive. They just didn't have the oomph to generate images. Did anybody play Pac-Man in 1980? That gives an idea of the quality of image generation in that era. Obviously, this is a commercial product, and they would have better. But the Apollo program had to decide for the simulators, where, for reasons I'm going to explain, they have to be able to see through the window, you need an optical system with models. And that decision drove a whole bunch of expensive things to create these amazing devices. This is TechWorks in Binghamton. That's about 2 hours northwest of New York City. And this is the city of the player pianos, the Link aircraft simulators. The Link Apollo simulators were made there. And the executive director for this, Susan Sherwood, her energy has got parts from the actual simulators at Cape Kennedy. Do you remember I talked to you about the cylinder? Can you see the cylinder there? This is one of the devices from that, and I'm going to explain how these different parts work together. This is Al Nagler. He got me started on this, and I decided I was going to research it more, so I went to Cellophane and couldn't find him in the day, so at night I went to his area and say, does anybody know where Al Nagler is? And he said, I am he. So we got together, shared emails. He told me about this gathering. Now, notice that this picture is tilted on its side. And actually, this device should be on its back. So at the threat of causing Al's hair to hang down, I'm going to tilt him sideways. And this is the actual orientation of the device that the astronauts look through. Now, there was a window in front of it. Remember, everything in the simulator was exactly the same. But without the window, this is something that created image that my eye looked at. And I have a name for something that creates an image my eye looks at, and that is an eyepiece. Some people say, oh, no, it's not an eyepiece, but what is different than that to my 32 millimeter Plössl other than a bigger apparent field of view and a bigger eye relief and a bigger size? So this optical system is basically an eyepiece, and I'm going to explain how that works. Now, some images came from film, and I'm going to go more detail in terms of the light shining through film later. They also had a model where something was on a cart and the TV camera got closer and closer to docking hardware, and they could practice docking in these as well. NASA wanted to do as much as possible in these simulators. There are a few specialized simulators, but most of the time, I think it's 85% was spent in these simulators, or the third one I'm going to talk about. Did I go too far? No. I doubt if any of you have ever seen a celestial sphere. This is a 27-inch ball that's black, and it has embedded ball bearings all through it. These are the 3 stars of Orion's belt. Rigel is a larger ball bearing that reflects more light than the smaller belt stars. And 3 stars were coated in gold to make them a little bit red, Betelgeuse and Aldebaran and Antares. And these were very accurately located on the celestial sphere. This was projected through all the optics that I'll explain in a little bit, and apparently the view was pretty attractive. But when the spacecraft turned, either because it was in barbecue mode where it slowly rolled to spread the heat around it, or the commander decided to change the orientation, the computers would sense what the control effort was, and it would calculate the new direction that this thing is supposed to turn, and it would turn it. So they would actually see what would be visible through the window at that time. Now there's a reason for it beyond just to please the astronauts. The Apollo capsules had a gyroscope. And in it you've got 2 spinning devices, and let's say this one points to Vega, and the other one could point to Capella. They're about 90 degrees apart in the sky. And as long as they stay pointing at that, the spacecraft can tumble all over the place, and they keep pointing at the direction, except they slowly need realignment. So there were 37 navigation stars, ironically not including Betelgeuse because there are lots of bright stars near it. And they had this map, and the astronauts could use it, and they figured, oh, I think we're at, say, Navi. Now, this is expanded because it's close to the north, but this is the W of Cassiopeia. And the center star for the Cassiopeia is called Gamma Cassiopeiae, but that was a long name. So the crew of Apollo 1 thought, why don't we make our own names? So Gus Ivan Grissom turned his middle name around and got Navi for the middle star of Cassiopeia. And I always think of that as Navi. There were 2 others that were given, and those names stuck perhaps because unfortunately that crew perished in the fire. I can't say I know exactly how the computer works, but I'm going to go through roughly. There was a program that would allow the spacecraft to be oriented so that the optical alignment telescope would point at a certain star so they can check the alignment. So what they would do is they would say, press the number for the program, and that would be a verb, and then they would press 03 for the star Navi, and they would press enter, and the spacecraft and the telescope would point at that particular star. So they didn't have to find the star. They could see it might not be exactly on the crosshairs. Then the astronauts would do tiny adjustments to get the crosshairs in the right place. Then when it was all ready, they would press enter. And the computer would remember the specific time it was done, the angle off, it was all connected to the computer, and it would update and say, well, this isn't pointing exactly to Vega, it's maybe 5 arc seconds off. And they would update it. An error of 6 arc minutes would be 700 kilometers at the moon. So the accuracy of pointing is quite important. So this is sort of how the system worked. But some people in NASA, especially in the early 60s, were worried that somebody nasty might decide to jam the signals to the astronauts. They didn't want that. So So the astronauts also had the capability of navigating on their own, although most of it was from ground sensors. And what they would do is they would have a separate sextant and find a star. I added the blue, by the way. They would find a star that was about to set on the moon or rise on the moon. They would line up a separate sextant, and they would go through the similar procedure of entering the code in 03 if that's Navi, and then they would press mark, and the computer would remember the exact time, and then it would calculate the new state vector, which is basically the 3 position coordinates in whatever system they used, and the 3 velocity components, and then they would go from there. Now the optical system. Remember I talked about the parts there? Okay, they had a choice of either using large lenses that would be very expensive and very difficult to get good quality, or mirrors. So they decided to use big mirrors, and Erlen Ward, who worked for Link Simulator Company, is pointing at this device. So that is a spherical mirror, and spherical means it bends this way, and it also bends this way. This is a beam splitter. The LIGO system has a tiny beam splitter in it, but this is a giant beam splitter, and somehow they process the one side of a glass, half silver it, so half of the light goes through and half reflects. And you can see that in this image. See how bright Erlen's hand is or finger is right there? Notice that the reflection is a lot less bright. That's because half the light goes through and half reflects. And I'll explain in a bit how that works. So this is a diagram that I made showing a ray entering the system, and it doesn't have to come at 90 degrees. It bounces off the beam splitter and half goes through. Then half of the other energy reflects, comes off the spherical mirror, then it hits the beam splitter again, and 1/4 of the original intensity reflects and 1/4 goes through. Now there are 2 problems with this system. You get less light coming out than you had going in. And also, you've got this ray that is extraneous, and they have to have really dark surfaces to absorb all the light that gets in from other directions. Now, this is a big diagram, and I'm just going to let you look at it for maybe a few seconds. Then I'll start explaining it. Okay, can I ask you to look at the lower right? This is where the astronaut is, and this is what he sees. Now can I ask you to go to the lower left, and this is a black celestial sphere with silver and red ball bearings. They also had a TV set that was the same shape, but I'll get to that in a little bit. So these reflect light. Now could you go to the upper right, and there's a bright light that is collimated. It's like it comes from one source shining on the black celestial sphere. Now follow the white light that hits this red ball bearing. And could you just follow this ray? Can everybody see where the cursor is? So the ray goes up, it reflects off the beam splitter. For now we're ignoring the part that goes through. Then it reflects back to a second beam splitter on the eyepiece spherical mirror. Then it reflects up to here, and it goes again through the beam splitter, and you get a ray coming in like this. Now let's look at the other ray. So this is the red ball, and you're also going to get a ray that goes a little bit to the right, and it bounces, same path. Notice that the 2 red rays come parallel. Well, light from stars comes at our eyes parallel. So the astronauts could see what looked like real stars that were infinitely far away. And if you have a window like this and you move your head back and forth, see, you can not see some stars, and then you can see some stars that are a long way away. But if it's a TV set, you just see the stars all in the same place. So it looked like the stars were infinitely far away. And this is how the system worked for Mercury, although it only got finished near the end of the program, Gemini, and Apollo. Genius. Okay. To the left is the device that has the cylinder on top, and it's got the celestial sphere in it. This is a cathode ray tube or TV set, and it went in here. Now, the images were combined together with another beam splitter, so you could add the two together. Now, this is a picture of one of the other TV sets or cathode ray tubes, and in the old style TV set, you had an electron gun. It fired electrons, and then a magnetic field and electric field would cause them to deflect and go up and down, and you get your TV signal here. But this is a spherical surface, so they had to adjust the signal, which required special electronics to do that. They also wanted this as bright as possible. Remember, 1/16 of the light gets to the astronaut's eyes. So you need really bright sources. And they could do that by cranking up the voltage, but too much makes X-rays. So they had a limit. I asked if they had special coatings, and I expected the answer was yes, and I was told no. It's the same coating on other things. I know nothing about this other than it's a complicated diagram where light comes through and it can deflect either to a right film or left film strip or the right film strip, and you can make all sorts of adjustments. It projects against a screen, and then a TV picture is taken of that sends into the TV. This would be used for large-scale pictures of the Earth showing sunsets and oceans and continents going underneath, or the moon as you approach it from a few thousand kilometers away. It was terribly trouble-prone, and apparently sometimes the heat caused the films to catch on fire, so they had to have rapid airflows past it, but that caused the film to shake, which means they couldn't get good focus. It was a real headache, but that worked. But to me, the ultimate part of teaching meal to land is this, which is a moon model. And it's a patch of moon that's about 10 kilometers across. It has craters in it. The original version was generic. Then later on, they made one that actually showed the landing site. Quiz, can anybody tell me which landing site that was? This is Apollo 15's landing site. And the actual landing site is behind this guy's head, but for photographic purposes, they have the map upside down, and he's pointing to some place that the astronauts never got near to. But this was an actual device, and this picture shows them putting that device in upside down, and the camera would get closer to it. Now, the camera was on a cart that was under control by the computers. So if Neil decides I have to go an extra half a kilometer to get out, what they did is the computer would calculate where this would go. It would move the moon model up or down, and it would get closer and closer. Anybody see from the Earth to the moon? This is a scene in it, and it shows horizontal lights or sloping lights like this and a lens like that. The reality is, based on my information, is the TV camera looked like this. And I'll explain what was in it. This is the head prism, and I could find no specific information about it. And I'm really frustrated at that. Not even a better picture than this. This came out of a paper. What I saw is the diagram for a Slater lens system that's based on this that Al Nagler worked on and authored. And this is 4 millimeters across, so the actual lens is maybe 1/3 of an inch, 8 millimeters. That size is what took the images. This allowed it to tilt from side to side or rotate. There is a problem with distances, that when you get close to this model, you might be looking here that would be underneath the lunar module, but maybe Neil would also want to look at a further distant place to see if that's a better landing place than right underneath. So they had Scheimpflug optics, however you pronounce it. And the key is they have 2 rotating series of lenses in here. And those computers were able to say, it's this close. Now we're getting to the point where the distance at the bottom is very different from the distance to the top. These would tilt as controlled by the computer. And this shows an image from Al Nagler's project where that is maybe 5 millimeters away from the lens, and that might be almost a meter. So that's an incredible depth of field because the focus is from here and there, and they get everything in between. This is the total device, and I think that's a 2x4 to give you the context of size. And it was to be marketed for aircraft landing and practice landing and everything, and I don't think it took off, perhaps because computers were able to generate images. Al told me that the lenses he used were similar to what was in the Nagler eyepiece, and I showed him a Nagler eyepiece and said, it doesn't look the same to me, and he said, turn it around. So I turned it backwards and looked at it against the light, and the Nagler eyepiece, this is the 79 version, I've just inverted it, is similar to the probe. Now, the astronauts would look through the simulator. They wouldn't quite see that good a view. And this probe was getting closer and closer. And then one crew of astronauts, not Neil and Buzz, saw this. What happened, and I talked to the guy, he saw a 2-inch long Florida cockroach, picked it up, had some double-sided tape, taped it upside down to the model with some legs still wiggling, and the astronaut crew landed, and they saw this. Now, I don't know whether the astronaut crew died, and sometimes missions they didn't do an abort in time and they died, or whether they aborted, or whether they just died laughing, but can you imagine with the tension in this simulator to get everything right and suddenly to see that? So, how good was the system? Neil and Buzz didn't like it that much, but later crews did. There are limited details through the simulator when close, nowhere near that good a view. They couldn't simulate the dust or the shadow of the limb, they could just have a box. A later system was better. So they also had a lunar landing training vehicle, and basically this rocket would lift it up in the sky with the commander in the very front. And then it would go into lunar mode when the turbofan engine carries 5/6 of the weight, and the other is controlled by the astronaut to simulate the lunar landing gravity. Unfortunately, Neil was flying this once, and he couldn't quite get it still for a landing, so he went back up again, and there was some mechanical problem, and he ended up ejecting, and surprisingly ended up going back to his office to finish paperwork when most people would just go home. So, true or false? Did the purpose of the simulators was to train astronauts? Answer, false. All the mission control people, all the experts in the different fields connected to many others would be part of this exercise. NASA rented a phone line all the way from the Cape to Houston. They had the time delay for the radio signal to reach from the moon, and they practiced everything, especially problems planned by the SimSup Dick Coos, and he and his crew found things that could go wrong with the spacecraft, and they had to practice the different challenges, and many astronauts said the simulator was more difficult than the actual landing. Interesting, when Smithsonian Magazine made an article on 20 people who made Apollo happen, he was the first one listed ahead of somebody named Lyndon Johnson. Notice the patches made by the astronauts for each crew. And there's something different about Apollo 11. They didn't have any names. The patch for Apollo 11 does not have any names on it because the crew felt this was an accomplishment, historical accomplishment, not just by those three, but the 400,000 people who worked on the program and all humanity. And it's the hard work by this crew of people who taught Neil to land. Thank you.
Okay, well, this presentation is about some of the stuff that I do when there are cloudy nights and not so cloudy nights. I like to build things. And as you can see, I've attached a finder scope to a drill so that, it helps you drill, straight holes. So really this is about how to focus telescopes and the things that you use. And why do we actually need focusers? Because you're not changing the lens, and the mirror is always the same size with the same focal ratio and focus points. The point is that all the eyepieces are different. And the main lens or the main mirror will always focus the image at a specific point, according to its focal length. But yet the eyepieces have 5 millimeter focal point, 25 millimeter focal point, 40 millimeter focal point. So you need to move the eyepieces, the various eyepieces, back and forth until those two focal points coincide so everything is sharp. So that's why we need focusers. This is a picture I took at the Eclipse down in Kentucky. There are many different kinds of focusers. I'm going to talk about this one. It's called a Crayford focuser. And if you can't buy a Crayford focuser, you can always, well, just print your own. Well, what do I mean by that? It sounds a little crazy. What do I mean by Crayford? What do I mean by print one? This is a basic Crayford focuser. And it consists of a tube that you put the eyepiece in. There's a ball bearing which rotates, which rolls here, and there's another one on the other side. There's another ball bearing here, and another one you can't see on the other side. And this tube will slide along those two ball bearings. This axle presses against the tube. So when you rotate that knob, it puts pressure, friction pressure, on this tube, and the tube will slide back and forth according to how this axle is rotated. Here's a spring. It just keeps the pressure on the tube. This is a 3D printer. Now, what does a 3D printer do? It takes a piece of spaghetti plastic, this white plastic, on this spool. It runs it through a heater. That's why there's fans on it. And that plastic is extruded out, that little tiny nozzle right there. We have a motor here which moves this extruder in the x-axis. We have a motor around the back that you can't see which moves this table in the y-axis. And there are two motors here which raise and lower this whole contraption in the z-axis. I'll get into that a little more in a second. Here are typical Crayford focusers. These I just got off, the internet, and they all have the same basic configuration. What you have, again, is the tube that the eyepiece goes in. There's that little axle right there. You can just see it with the focusers. And you rotate this knob. That axle rotates, and the whole unit rolls up and down against the ball bearings, which are inside that you can't see. These are a little different because they have a coarse adjustment and a fine adjustment. This coarse adjustment racks it in and out, and the fine adjustment is usually a 1 to 10 gear reduction, so you get very, very small adjustments. So what do? I use a program called Machine Shop, and there's a lot of programs out there. You don't have to use this. There's SketchUp. There's all kinds of different free stuff on the internet that you can use, and you can design the part. It takes a little learning curve. You got to be able to do it. And I want you to look at, where are we here? Okay, I want you to look at this part here, this horseshoe part, and I'm going to go back one slide. Whoops, wrong way. Hang on. Never mind. Previous. Okay, remember this shape. Previous. Come on. You can do it. You know what? I was holding the wrong mouse. Someone else has a mouse here. All right, can I do it this way? All right. Where is the mouse? There you go, just go back one. Yeah. Just roll it? Okay. So let's go backwards then. And, okay, let's go, okay, remember this piece right here? This piece right here? That is this plate here, that plate right there, that plate right there, and of course you can't see it here because it's underneath. Okay, I got to get used to this one now. Okay, now remember I said that that z-axis raises up and down. That's because when you make your model, you have to slice it into about, well, it depends how big it is. This one is, I guess, about 100 slices, so that the plastic is laid down in one layer with the X and the Y, and then the Z-axis moves it up one notch, and more plastic is laid down, and the Z-axis moves it up again one notch, and each of those notches is a slice in the model. So you have to slice your model, and I use a program here called Cura, and you don't have to use this one. There's a whole bunch of other ones out there. It doesn't really matter. And if you look here, layer count, 96. Estimated time to print it, 1 hour. This is a program called Repetier, and it is the one that I use to actually control that machine. It talks to the machine, it tells it what to do, and it will lay down all those different layers in the model. When it's finally made, it'll look something like this. Now, these bars that you see here, those crack out. Those are not part of the model. When the z-axis gets up to this layer here and starts extruding this layer, there's nothing below it to support the plastic, so that'll sag. The program puts in these little support bars so that the plastic has something to rest against as it cools. And when it's finished, you just take a screwdriver and you just crack those things out. And there's the model that fits against the back. And this is a little movie, I hope it works. There we go. That shows the heated extruder here laying down the melted plastic as it builds up the model. And when it finishes that layer, the Z motors will drive it up 1 fraction of a millimeter, and it'll start again. So this is basically what it looks like when the printer's working. It's extruding plastic out onto that bottom bed. All right. Okay, so there's that piece. Those little supports have all been cracked out of there, and now we're tapping holes. This is where roller bearings are going to go. Those little roller bearings that help guide the tube that holds the eyepiece. There's bearings go in here and bearings go in here, and I'm tapping threads so that the bolt will hold the bearing in place. And these are the roller bearings that fit in the slot. These are what roller bearings look like in my hand, and this is what they look like in a diagram. There's little ball bearings in a race, so that the outer part will rotate almost frictionless with respect to the inner part. Now this might be a little hard to wrap your head around, but we need to put pressure against that spring that I showed you way back. You need pressure against the tube. This bolt screws into here. It floats in this member here. So the bolt really has nothing to do with this block. When it's screwed in all the way, the end of this spring, which is compressed, will press against the shoulder in here and push that whole block forward so that the axle is pushed against the tube. It's kind of hard to figure when you can't see what's going on inside, but you know, that's basically what happens. Here's my completed focuser, and I've added a couple of extra things. I've added a tension adjustment so that if you put a heavy eyepiece in, it doesn't pull the tube. And I've put a eyepiece lock in there with a little nylon bolt so that your eyepiece doesn't fall out. And you can watch that work. Works very nicely. You can see how that moves the the tube in and out, nice and smooth, right? Okay. Now, the next project is a different type of focuser. It is a helical focuser. Now, I took this picture a year and a bit ago, I guess, less than a year ago. But since there's some really good astrophotographers in the group, I'm kind of embarrassed to show some of these things. But anyway, this is a helical focuser, and it can be as simple as plumbing parts that you buy at Canadian Tire. When this part goes in the telescope, this part holds the eyepiece, and when you rotate this, it has the threads on it. Screw it in, screw it out. It has a limited range of motion, but costs you $1.50 to make. Not too bad. I built something a little different, and this, again, has these roller bearings on it. I'm going to go back to the plumbing part one for a second. These threads are on an angle. That's why it'll move up and down when you rotate it. That roller bearing is on an angle, so that when you rotate the tube, it'll thread itself up and down within the focuser. So this is what the part looks like when it's designed. Here you can see the 5-degree angle with respect to the horizontal. And this is my completed focuser. And hey, lucky break. 1¼ inch plumbing piece from Canadian Tire, fits an eyepiece very, very nicely. So let's see a little closer up image. There's my roller bearing, there's the bolt holding it in, it's pressing against the tube, and once again we can watch how that works. You can see how it smoothly screws in and out, right? Just like that. All right, so that is the first part of my presentation. I have another second part to go, but I stop for a second. If you want to shout out any questions, I'll repeat them so the online audience can hear them. If anybody wants to jump in for a second and just ask something, I'll be happy to answer that before I proceed. Just keep going. Yeah, please. Who's asking? Okay, go ahead.
What kind of plastic are you using?
What kind of plastic?
Yes.
The plastic that I'm using is called PLA. It's called polylactic acid. Lactic acid is the same chemical that makes your joint, your muscles hurt when you exercise too hard. And so it is biodegradable. It is organic. And it won't last 1,000,000 years at the bottom of the ocean. So it's very biocompatible, if you want to call it that. Okay, please.
In your first Crayford focuser,
Yeah.
What was the advantage of actually making the eyepiece tube, building the eyepiece tube, as opposed to using a tube like you did in your helical focuser?
I don't know. I just wanted to do everything. You know, I mean, once you're building something, you keep going, you know. I'll be taking the easy way out in a minute here. You'll see that. Please. Turn on the mic. There you go. Okay, good,
thanks.
good.
Yeah, one comment and one question.
Sure.
The question is, can you share the STL files?
Yeah.
Okay.
Absolutely. Give me your email, and I'll email
talk
it to you
afterwards about it.
Yeah, that's fine.
And the other one is, I live in Newmarket, and the library there has 2 3D printers
Right.
that you can basically get time on, and
Yeah,
I
yeah.
believe that other
Yep.
libraries do the same.
Yep.
So it's a nice, convenient way
Yeah.
to do it. They only charge you for the material.
Sure.
I think it's like $1.60 a meter or something, so
Okay.
it's pretty cheap. You probably got about, what, $5 worth there? Or something?
Well, that was about 4 meters.
Yeah, so $6.50.
Yeah. The problem with the library, they have a time limit. It may be only an hour. Yeah. Some of these things can take 2 or 3 hours to print.
Yeah, I mean, I've printed for 4 or 5 hours.
Exactly.
And on Friday, they have an all-day
Okay.
long print session, so
Cool.
you can do
All right, you got it then. All right, good. Any other questions right now? Okay, I'll keep going. How do I get to the next presentation? Just get out of here? All right, good. So, I took this photo about 3 years ago in August. And if you're familiar at all with the sky, this is Sagittarius right here, and a couple of Messier objects right here. And let's, I've got a slide that shows them just a little clearer for you to see. There's Sagittarius, the teapot of Sagittarius, and there's the two nebula. And you can see the Milky Way comes out of the spout of the teapot like steam rising out of a kettle. It's kind of nice to see. You can see it as a time exposure because there was a boat going across the water here. Anyway, I like building things, as I was saying, because it's really interesting for me. And if you need something, obviously you can borrow it, buy it, you know, you can build it. I like building things, and I think building's fun. It can be frustrating, you know, at times. Things can, you know, blow up in your face, but for the most part, it's an enjoyable exercise. Anyway, why in the world would you want to build something when there are so many high quality pieces of equipment that you can go out there and buy? And there's some amazing pieces that you can go out and buy. Why would you want to build it? Well, for all these reasons. It's fun, it's creative, lots of cloudy nights, especially this winter. It feels good when you build it, when you actually build something that works. My main problem is I like it to solve an issue. I'm observing, there's something that's really annoying me, and I figure, you know what, if I can solve this problem, it's going to make observing a lot easier and a lot more enjoyable. So what kind of problem am I talking about here? Well, have you ever tried to focus on a moving object? You touch the telescope, it jiggles. You touch it again and it jiggles again. And you turn the focus and maybe it doesn't look quite right and you want to go back a bit and it's still jiggling, and it drives you nuts because you can't focus the telescope on a jiggling moving object. So what did I want to do? I wanted to build a motor so I could hands-free focus the telescope without touching it. And that way, at least I had an advantage. This is a typical microfocuser. If Blake were here, he would recognize that he got this for me from the estate of Jeff Garrity. And this part here screws into the telescope. This part here, the eyepiece. And just like I showed you on some of those other ones, there's a 10-to-1 gear reduction on here. Why do I call it hocus pocus? What's so hocus pocus about it? Well, it actually is pretty involved. You need to know a little bit about electronics, expensive parts. You need to understand how to use those computer programs that I showed you on the previous presentation. CAD means computer-aided design, CAM means computer-aided manufacture. I'll call them advanced tools and equipment. You have to be able to build circuit boards and then troubleshoot them when they don't work the first time. This is what you're going to need to build this thing. A stepper motor. I'll get to that in a minute. You need a driving circuit for the stepper motor. You need a gearbox assembly for the stepper motor. Then you have to have a telescope interface. Then on and on and on and on and on. There's all these little parameters that need to be worked out, and lots of tools, electronics tools, drill presses, milling machines, like all this kind of stuff. So what's a stepper motor? Well, a stepper motor essentially is a motor that has 4 coils in it, and when you apply a pulse of electricity to each coil in succession, the motor will turn in discrete steps. The nice thing about that is you know exactly how far that motor turns per step. So you can have a computer count the steps, or you can have a computer tell that motor how many steps to turn, and it knows exactly how far it's gone. Why is that important? Well, your hard drive has a stepper motor in it. How does the computer know where to read that spinning disk down there inside there? It remembers I have to tell the stepper motor to move here, to move the read-write head a certain place to pick up the data on the disk. Your go-to telescope has stepper motors. You program into the hand control, which is essentially a computer, what you'd like to watch, or look at or observe. Telescope knows where it's pointed to start with and will turn in discrete step motion to the place you want it to be. So stepper motors have a lot of uses in all the daily life. They're used a lot in cars to open and close vents, things like that. They're all over the place. Okay, so let's watch one work. Here's that driving circuit I talked about. So you can see that the motor's working here. It's rotating. I'm applying pulses to each coil in turn. And what I can do is I can adjust the rate of the pulses. And that will speed up or slow down the stepper motor. So here we're really giving it a lot of pulses. And now, look, you can almost see the individual ticks. See each little tick? That's each coil being energized in turn. And then you can speed it up. And if you want to, what you can do is you can then send pulses in the opposite order, and it will go the other way. So that's what a stepper motor does. Very, very important, very useful. Okay, what is a microcontroller? Well, we got to somehow control the stepper motor. So a microcontroller has a little bit of program space in it, a little bit of memory space, small, inexpensive, easy to program. All that stuff has input pins, output pins, all these things that you define when you program it. Very simple. An input pin, what would you use that for? Well, if you press a switch, the input pin will sense that a voltage has changed. Well, the program you put in there says, you know what? When a voltage changes on that pin, I better do something like send out a pulse to the motor. That's the difference between an output and an input pin. That is a microcontroller. Fits in your hand. This is my original motor controller box. Look at this thing. It's enormous. It has a timing clock module on it, and you change the pulses per second with this little control adjustment over here. It has 1, 2, 3, 4, 5, 6, 7, 8 output transistors in it. It's got logic chips in it. It's a zoo, and it took a lot of time to build, and it was a big deal at the time. This is what the circuit diagram looks like. Crazy. You don't have to understand what it does, but then again, there's the 1, 2, 3, 4, 5, 6, 7, 8 output transistors. And this is the circuit board that I had to build. I had to design it and mill out the circuit board, and it worked great. But it's big, it's heavy, and it uses a lot of power. Let's watch the pulses changing. Here's the driving circuit. This shows you on an oscilloscope how the pulses to the motor will change when you adjust down at the bottom. So let's stop. Oops. Oh, come on. Previous slide. Let's do that maybe over here somewhere. Okay. I don't know if you can read it. This says 2 volts. That means 2 volts for every little box here, every little division. So here you can see we got 5 volts, drops to 0. Time goes by. 5 volts, drops to 0. Time goes by. Those are the clock pulses to tell the motor each step how to turn. All that stuff in that great big box that I showed you, welcome to 2019, okay? This all fits in your hand. This little chip right here, that's got those 8 big driving transistors in it. This thing, this has all the logic in it that says how fast and in what direction to run the motor. There's actually 8 little lights on here which shows you when the pulses are being sent out. So, I just went out and bought that. $3 for both those things. It's unbelievable. It took 4 or 5 weeks to get from China, but you know, for $3 or $4 you can do that. And less time, less cost, less size, less power, less debugging and troubleshooting. This is the program that you use to put the information into that microcontroller. And as I told you, you decide. Button 1 is this. Motor pin 1 is this. We're going to say button 1 is an input. Button 2 is an input. Motor thing is an output. So I'm not going to bore you with the details, but you lay out the whole pattern of pulses to the motor in this program, and then you load it into that microcontroller through a little cable. Well, proof of concept. Let's watch that work. Okay, so there's those little lights there showing each pulse going to the motor coil, and you can see that it is turning. And if I changed it so that the pulses would go in the opposite direction, the motor would turn in the opposite direction. So that's basically what we got going on there. Now, here's that focuser, here's that motor, and, well, just as an aside, a number of years ago, we used to have meetings at the DDO on Saturday nights, and people would present stuff and be interesting little topics and things. And I gave a couple of presentations about things I had built, which a lot of people were horrified because I used to drill into various pieces of telescope equipment. One fellow walked up to me after one of the meetings and said, "How could you drill into that telescope?" And I said, well, for that one, I think it was a 3/16 inch bit, as I remember. But anyway, the point is that this is far too nice a piece of equipment to drill into. It's not in me. I can't do it. And I needed to design something that actually fit on it and clamped on it instead of drilling and holding it in. So that's where this piece of lucite comes in. You can see it's split here with a hole, and this piece of lucite will fit on this shoulder right here. This is the drive gear attached to the motor. This is a drive timing belt, and it will wrap around the coarse focusing knob. So let's see where that goes. There it is. So it clamps on, tightens up with those wing nuts. Lucky for me, those little teeth on the drive belt really nicely fit the teeth on the coarse gear. So let's see how that works. Here's the split adapter, and you can see how it, opens and closes, and that will snug up against the shoulder on the focuser. That's how it tightens up. And of course, it's spring-loaded so that it stretches that timing gear so the timing gear's tight. There's also a curved slot at the back there so that it can rotate around an axis. All right, good. So let's watch it work. Here's the power. Here's the control box. Turn the power on, and we can turn it one way. See how it goes? Turning the coarse focus adjustment, just like that. So this is a hands-free adjustment now once this is attached to the telescope. So at this point, I'm going to stop and say, any questions yet? Yes, sir.
I think that's wireless.
Wireless, yeah. Well, that means that the battery's got to go on it. It's heavy, But that's you could do that.
How much?
Well, there's two. You can't see it, but there's two 9-volt batteries under here. Like on the bottom of this thing, there's two 9-volt batteries. You'll see them in a couple. Motor for the current. Yeah, the actual microcontroller, milliamps, 5 milliamps. You need current. Yeah, you do need current. Okay. Any other questions just for a sec? Anything? Nothing? I'll keep going. No one's going to ask me why I didn't turn the fine adjustment, the fine coarse adjustment? No? Okay. Lights? Well, I thought somebody was going to ask why I didn't attach it to the fine adjustment. Yes? Well, I thought you might ask that, you see. So what I did was I had to add another piece of lucite and another piece of aluminum and another hunk of this bracket. Here's the two 9-volt batteries underneath. You can see that down there, right? But in fact, yes, I did attach it to the fine focus control. And you can see it turning, right? It's very, very delicate. All right, so you can see it turning. All right, and I'm not going to do it the other way, but it does in fact turn the other way. Okay. Okay. I mean, this is starting to look crazy already. I mean, if you go back and look at this, we got screws and wing nuts, and we got lucite, and we got more lucite, and we got bolts, and we got plates, and we got brackets, and it's like it's getting way too complicated. I mean, it's crazy. So what am I going to do? What am I going to do, right? Okay, well, I'm going to start from the beginning. And what I did was I built a brand new focusing mount. This one was the prototype. I printed each of these little pieces that you see here individually and glued them together with crazy glue according to all my measurements. I then fit it to the focuser, and I could see where it could be modified, adjusted, played with a little bit. So I went back to the computer, I changed the files, I changed things here and there, and when I finally got it the way I wanted to, I printed it as one single, complete, solid piece. So this is the production model, one solid unit. And this is my printer, again, working. It can show you, you can actually see it. It's not the best video in the world, but it shows you how the bed moves, and it shows you how it goes across and lays down the plastic in layers. Builds it up. All right, okay, enough with that. We've seen that already. Okay, so let's watch it work. Okay, you can notice that rounded shoulder. That's where that's going to sit. There's a tension adjust knob that can come out. Let's take that out. Put it down. Let's have it roll off the table. This coupling goes on. Everything's press fit. Yep, there it goes. On the floor. There's my head. There's my head. Okay, so we can screw that tension adjustment knob back in. It holds everything nice and firm. Okay, I did not need really to make this piece, but I did oh, there goes the next one. Just for fun, I put on an additional bracket to hold it on. It's not necessary, but I thought, well, just for solid support. That'll screw in. Let's pick that other one off the floor. Okay, retrieved. Now we get that motor control box. We think we'll just plug that in now. There's those two 9-volt batteries I was telling you about. Turn it on, and can you see it work? If you look right here, you can see the light as it's rotating, right? It's a little hard to see, so what I'll do is I'll show you a close-up. Here's a close-up. You'll be able to see it better. There it goes. There, you can see it a little better now. You can see it. Just like that. And then, of course, it does go the other way. Okay. So, That's basically what I have been up to. And I will now answer questions for you if there are any other questions. All the questions have been asked. Okay, go ahead.
How long was it sort of from concept to end? Like how many hours, days, weeks?
Oh, that lucite one, the original lucite screw-on one, probably took about 2 weeks. Just, in the evenings, just measuring and, cutting and gluing and, stuff like that. The 3D printed one probably took about 1 week to do. I had to think about it, had to measure, lay it out in the programs, design it, mess it up, learn how to use the program, all that kind of stuff. Yeah, and usually you have to print it a couple of times. That one probably was 4 or 5 hours to print, and so I started at 11 o'clock and go to bed, and of course overnight the power went off for 10 seconds, and okay, got to do it all over again, computer's now on the welcome screen, all that. So probably a couple of weeks, I would think. Yeah, so it's just a good waste of time. Is that it? All right, folks. Oh, one more? Oh, okay. Sure. You can, if you're embarrassed, you can always come up to me after the presentation and ask. It's fine.
Yep. How do you deal with if you want to make a big movement? Because in your second design there, I don't see any way that you could spin it manually or at a higher speed.
That's the downside of the second unit. The first unit, because it's spring-loaded, you can shove the spring, it'll loosen up the drive belt. You can play with the course adjustment. This one, it's kind of locked in. Yeah. No clutch, that's right. There's no clutch.
The belt one, when you reverse, was there any play?
No.
I could see on the suction one there wouldn't be any play.
No.
Nope.
No, it was tight. It was good. It was like it's gears on both sides.
Yeah.
Right? There's the splines on the course adjustment, which grab the teeth on the drive belt.
It was direct.
Oh yeah.
Oh wow.
It was like direct drive. It was good. Yeah.
Any schools or university? Okay.
No. I finally made it here. I was supposed to give this talk in February, but there was a snowstorm and they canceled the night. It was one of the only 2 nights they've ever canceled. Then I was going to give it in April, and the computer did not play nice. And I almost went home tonight, but it worked out. It all worked out good. All right, cool. Thanks, guys.
Okay, ready to go? All right, so what's up for the next little while, for the next month or so? So, let's see. All right, our next meeting is going to be in mid-July. We go to 1 meeting a month. So our next session is here at the Science Center on Wednesday, 17th of July. And the famous TBA will be presenting the sky this month. Also, Manuel Guerrero talking about imaging the planets at latitude 10 degrees. And Frank Dempsey will be talking about solar observers and contributing to the AAVSO solar program. Okay, let's see. Make it this way. Our next solar observing session is going to be here on the Telescape on July the 6th from 10 o'clock until noon. Usual fashion, Sean will make the announcement of go or no go. through our various communication ways, either on Friday night or first thing Saturday morning, and hopefully we'll have some good skies for this particular session. And if it is clouded or rained out, then the backup date is going to be the following Saturday. Okay, observing. Our monthly observing sessions for members will be Dark Sky Star Party at Long Sault Conservation Area, the first clear night of the 1st through the 4th of July. So you've got both national holidays in there somehow, and that should be interesting with fireworks and all that for that period. But anyway, there we are. So hopefully we'll get some good skies so that you can take a look at deep sky objects during that period. And then the following week will be the City Star Party at Bayview Village Park, first clear night of that Monday through Thursday, the 8th to 11th of July. Okay, we're doing a lot of outreach, of course, and so at this time of the year, we've got things going on across the GTA. On the 5th of July, the Friday night, we've got Millennium Square program going on from 6 p.m. until 11 p.m. And again, the maps to get there are online as well as in scope. And also, we continue to have programs at the David Dunlap Observatory. The next family night at the DDO will be on the 22nd, this coming Saturday, and 9 o'clock to 11:30. I can now tell you that we'll have our annual awards picnic and open house at the DDO on Sunday, July 28th. Starting about 2 in the afternoon and finishing around 7. We'll have tours of the DDO administration building and the 74-inch telescope and perhaps the grounds of the DDO, the awards presentations and a potluck barbecue and a few other things. And again, the program hasn't really been finalized yet, but that will all be online on the center website in the next little while. At the General Assembly last weekend, I did manage to get one of the door prizes that we'll have for the open house. It's an autographed copy of David Levy's newly published autobiography that was published by the RASC. And David very kindly signed that for us. So that's something to get a chance for. Okay. We do have our dark sky observatory, the Carr Astronomical Observatory near Collingwood, and again, you can book space online for that. And the CAO committee is also at the point of being able to offer observing slots on the Sue Laura Observatory telescope. And when you make your bookings for the CAO, you can also put in for bookings for time on the SLO as well. And there's a whole bunch of things that are going to be available online in the way of information on how to operate the observatory and so on. If you do intend to use the SLO, you have to be able to do that without help from the supervisor, because the supervisor on site will have other things to do, including taking care of the telescope in the Jeff Brown Observatory. So again, there will be information about that coming available in the very near future. For the folks who are here for the first time, one of the benefits of membership is the telescope loan program, where you can borrow pieces of equipment for extended periods and get to familiarize yourself with the equipment, and that way you figure out what type of telescope observing equipment is suitable for what you want to do. So we have, let's see, one of our managers here tonight, Peter. So if you'd like more information about the loan program and the instruments that are available, please speak to him after the meeting. And finally, the meeting after the meeting, It's going to be a quick trip over towards Mount Pleasant and Eglinton before the kitchen closes, but we do gather at the Granite Brew Pub at Mount Pleasant and Eglinton after this meeting for a conversation, food, and drink. So again, you're welcome to join us there after the meeting. And that is it until mid-July. Oh, a couple of things, yeah, are on Macnaughton.
There were problems with my handling the video at the GA. I would really like a clean video of my talk to send to people I talk to about it. Is there any chance I could do a 1-minute version from where the computer is either now or if people can leave quickly? But it's really important to have one clean video.
Right. That's something you'll need to talk with Andrew and company about, okay? Yeah, Tom Luton?
Cards for
Yeah. Right. Right. Yeah. There are cards up at the front that will be asking people to sign for Charlene Norgrove's family and to get well for Bhairavi Shankar, who is a member of our DDO committee. Bhairavi was T-boned while driving on Monday. She's pretty badly shaken up, but fortunately not seriously injured. But she is feeling the impact of that particular incident. So we'll send a get well to her. Good wishes. And anything else? The picnic at the 28th of July, that's just a matter of showing up, okay? We'll probably try to do something just to get an idea of who's coming. Again, that's got to be worked out yet. We haven't got all the details ready. But certainly, you know, there is limited capacity in the buildings for tours, so we'll have to figure out how many tours we're going to run and so on. So if we can find out how many people intend to come, we can plan out a little bit better. Okay? I think that's it for now then. So we'll see you on July 17th and safe trip home, everybody.